So how does this thing come together then? F of 0 was 0, so that's 0. F prime is 0 is 1. 1 factorial is 1, so I get x. F double prime was 0. F triple prime was negative 1. 3 factorial is 6. Right, so you can imagine, you can already see the next one will be 0, and the next one will be plus, so that would be 3 factorial, 4 factorial, 5 factorial, right? X to the 5th, 1 over 120, dot, dot, dot. There it is. Yep, okay. So just kind of firming this up a little bit. And so you can imagine how that would continue. Now, how would you write that as in summation symbols? How would you write that closed form for that series? What's true about every single one of these things? What are the main numbers involved? All those numbers involved, all the powers and factorials are all what kind of numbers? Odd numbers. How do you represent an odd number? Nope. How do you represent an even number? 2n. How do you represent an odd number? 2n minus 1 or plus 1, right? Whichever one's going to make sense. So if I start this thing at 1, for example, will that work? Let's start this thing at 0. Let's make this easier. So what's going to happen here? This is going to be x to the... So like for n equal 1, it's going to be, n equals 0, it's this. N equal 1, it's got to be this. 2n plus 1, right? So twice n would be 2 here, and then plus 1 would be 3. This is n equals 2, so 4 plus 1 is 5, right? And since you got this repeated number in there, once you know this, and there's one little piece I still need. And then what's that's got to be? To the end, because I want the first one, the 0 term, to be positive. Cool. Whew. So let's do this. I want you to try what we just did, do it for cosine. And then we're going to verify what you got by working with what we have here for sine. So do this whole procedure for cosine.
Around a equals 0?
Yes, around a equals 0. So we can compare the two. should be off the heels of what we did. This is going to be a lot of very similar stuff here, right? So if a 0 here, that would be 1. So you see how it's kind of offset from that. All the 0 terms there are not going to be the terms that show up here. F prime is 0. F double prime is 0. So we see the same kind of pattern in the numbers showing up, but they're just offset by one step. So when you go to build this, I'll have f of 0 plus f prime of 0, x double prime of 0, x squared. And of course, these are just because I'm using a equal to 0 here, right? In general, it'll be x minus a. So we'll get f of 0 is 1, prime of 0 is 0, double prime is -1, so -1/2 x squared, plus 0 plus 1, and this will be 4 factorial, so this will be 1 over 24 x4. How we doing? Okay, cool. And again, this is 1 minus 1 over 2 factorial plus 1 over 4 factorial. Oops. X squared is 4. So what's that going to look like in closed form?
X to the 2n over 2n factorial.
And then of course the vector. Now if I take do that, and that was the power series representation of sine, right? So the derivative of sine, of course, is
Cosine.
I better get this, because that's the power series representation of cosine, right? So sure enough, when I do this derivative, this doesn't really care, right? It's just a constant. What happens in here, what happens? Actually, let's do this over here, because there is a little bit of something you got to be careful about. Yeah. So when I take this guy's derivative, this will be -1 to the n. What happens in here? What happens right here? What's the derivative of this?
2n plus 1.
Good. So the 2n plus 1 comes down. X to the
20.
and 2n plus 1 factorial, of course, hopefully we're all cool with just pluck that first piece off, right? So it cancels with that piece. And that looks very familiar. Right? Cool. See, and that's why I don't like a book. I think I remember this from that. Maybe I'm talking shit now, but sometimes they change that to 1. They really don't have to. In this case, I don't want to, because that first term is not 0. I don't want to change that index to 1. It's not a product of the derivative. It's just that sometimes they change it to 1 because the first term happens to be 0 when you take the derivative. Do you really have to do that? No. Mathematically, there's nothing wrong with adding 0 to it, right? So I don't want you to think that it's the product of the derivative that changes that index. It's just they don't want to have a 0 number show up. Who cares? Okay. So why don't we try this? So this is supposed to be cosine thing. So, and it's supposed to work really well close to what? Close to 0, because that's the a that we chose, right? If I wanted to work really well close to 30 degrees, I would have built it around pi over 6. Would have made the a equal pi over 6 and all this mess here. It would have worked really well around that. So let's say I go out to this far. If I stopped at that third term, I better put a value in that's pretty close to 0, right? So let's try cosine of 0.001. What's your calculator have to be in when you do this? Radians. Right, radians are true numbers. Degrees are numbers we made up. So almost always, some teachers might throw degrees in, but if any of you had taken physics, it's sort of like a physics teacher doing feet. Ain't gonna happen. They're gonna use metric, right? So here, you gotta use radians in here. So somebody help me out. What's cosine of 0.001? Make sure you're in radians. And then somebody else do this. So what do you get for this here? Yeah, 9999995. I think, right? And if you do that, 1 minus 0.001 squared divided by 2 plus 0.001 to the 4th divided by 24. You get the same damn thing. Yeah. Because I used the input that was pretty close to 0. So I would expect this to be pretty good. I don't have to go much further than that. Do you guys see how this concrete